Hello, Bhavana. Okay. So Bernoulli's equation. Bernoulli's equation is derived from the Newton's second law of motion. F is equal to ma. F is equal to ma ni you can apply it in two ways. For example, if we have flow in this direction, these are the streamlines. You can apply F is equal to ma along a streamline, or you can apply F is equal to ma normal to a streamline. Appudu you will get two equations, and the equation which we use 99% of the times is this one. So అందుకే one of the assumptions for Bernoulli's equation is flow is along the streamline. So Bernoulli's equation is only valid when you are applying it to a same streamline. For example, two streamlines untai, you cannot take point 1 here and point 2 here. Both of them should lie on the same streamline. And it is applicable for steady flow. And the flow should be incompressible. So incompressible flow ante enti? Incompressible flow means the density field is relatively independent of temperature and pressure. So the density does not change much with temperature and pressure. That is incompressible flow. So these are the main assumptions we make while deriving the Bernoullis equation. Equation derive jayano, but you can find both these equations in any textbook, any fluid mechanics textbook, along a streamline and parallel to a streamline. So along a streamline, we know that fluid is going to accelerate, but normal to the streamline kuda there will be an acceleration because of centrifugal force. So whenever there is a radius of curvature, whenever a particle is traveling in a curved line, it will experience an outward force, which is always directed away from the center. So e curvature ki the center aithe, there will always exist a force which is directed outward. That acceleration is denoted as an, the normal component. So you have a tangential component and a normal component. Tangential component use చేసినప్పుడు you will get Bernoullis equation along a streamline, and it is represented by this equation: P plus half rho v square plus rho gz is equal to constant. And also one more assumption you are making is the frictionless flow. That means there are no losses. There are no losses. Now let us look how this equation changes when there is a pump or a turbine or when there are losses. So let us say you have a system and there is a pump. This is one point and this is your point 2. And the pressure here is P1, P2. Similarly V1 and V2. So P1 plus half rho V1 square plus rho GZ1. This should be, and plus eta WP should be is equal to P2 plus half rho V2 square plus rho GZ2 plus WT by eta T, and this is eta P plus HF. This is the most generalized form of Bernoullis equation, which also takes into account the presence of pump, turbine, and also losses. So if you look at this term accounts for the pump with the energy which is input to the system or input to the fluid by the pump. And always remember units are very important. So WP is the work input or power input So eta WP is the pump input per unit mass of fluid. The entire equation, each term of the entire equation corresponds to unit mass of the fluid. So similarly, WP should also be corresponding to the unit mass of fluid, work input per unit mass. And then on the other side, you have WT divided by eta T. Eta T is the pump efficiency. And similarly, WT is the work output obtained from the turbine. WT is the work output obtained from the turbine. And eta T is the efficiency of the turbine. Once again, WT should be the work per unit mass of the fluid. And HF corresponds to the losses per unit mass of fluid. So far ఏమైనా డౌట్స్ ఉన్నాయా about the Bernoullis equation and the meaning of each term? Okay, let us carry on with the problem. So this one. Go through the problem and you can also try the problem. I'll give you 3 minutes. ట్రై చేశారా ఎనీవన్? ప్రణీత్? Okay, let's try it. So ఇది మనకి ఇచ్చిన సిస్టమ్. At this point, the pressure P1 is 120 kPa. And at this point, the pressure is 240 kPa. And E height is given to be 2 meters. And this height is 10 meters. And they have also mentioned that the diameter of the throughout the system remains constant. So what is the significance of this? We'll find out after writing the equation. So P1 by rho plus V square by 2 plus GZ plus GZ1 is equal to P2 by plus we also need to add the pump work. So eta into WP is equal to P2 by rho plus V2 square by 2 plus GZ2. Now let us take this as the reference plane. So if I say Z is equal to 0 here, then over here it is going to be Z2 is equal to 12. So Z1 becomes 0 and Z2 is 12 and G is 10 given in the question. And efficiency of the pump. They haven't mentioned anything about the efficiency of the pump. And they also said neglect frictional losses. So you can take the efficiency to be 1. And coming to V1 square and V2 square. From the continuity equation, we know that V1A1 is equal to V2A2. But in the question, they have mentioned that A1 and A2, area remains constant throughout the system. So you'll get V1 is equal to V2, which means both of these terms will get cancelled. And from here, you know WP. WP is equal to P2 minus P1 by rho plus GZ2. And what is the flow rate they have mentioned? They have mentioned the flow rate is 36 meter cube per hour. So WP is 240 minus 120 divided by 1000 into 10 power 3 because they're given in kilopascals plus GZ. G is 10 and Z is 12. So I get WP as WP is 240 kilowatt. Sorry, 240. Yeah, it's 240 watt per kg of fluid. Always remember every term in the Bernoulli equation corresponds to per unit mass of fluid. So WP will also be per unit mass of fluid which has been transported. But now you want to calculate it for 36 meter cube per hour. So 36 meter cube per hour is nothing but 36 into 10 power 3 kg per hour. Sorry, this is joule per kg. So this is 36 into 10 power 3 kg per hour. So if you want to convert it into kg per second, you divide it by 3600. And from here, So this is 10 kg per second. So this is your flow rate. The mass flow rate of the fluid through the system should be 10 kg per second. And you know that for every kg of fluid, you're going to spend 240 joules of energy. So what is the power required? The power required is the energy into the mass flow rate, which is 2400 kilojoules per second or 2.4 kilowatt. Is the approach clear to everyone? Pranit, ఓకేనా అర్థమైందా? ఓకే. So we'll look at another problem. Okay, so before we go to the next problem, let us look at a concept called friction factor. What is friction factor? Friction factor is nothing but tau W divided by half rho V bar square. So it is the ratio of shear stress at the wall divided by the average kinetic energy of the fluid. So higher the friction factor, the greater are going to be the losses, irreversible losses because of friction. So the friction factor is dependent upon the Reynolds number and also the pipe roughness, relative roughness, which is given as K by D. So you can find a Moody, there is a chart called Moody's friction factor chart, which is plotted for, I think, log F versus log Reynolds number. And the chart looks like this. So you have log F and then log NRE. And can anyone tell me what is the value of F in case of laminar flow? So yes, 16 by NRE. So the graph is at low Reynolds number. When we have laminar flow, the graph is going to look like this. So it's going to be a straight line with a negative slope. And as the Reynolds number increases, there is going to be a discontinuity here. And we get several curves like this. And each curve corresponds to a particular roughness or relative roughness, K by D. And what you will observe is that at a very high Reynolds number, the friction factor depends solely on the roughness. That is, it is no longer dependent on the Reynolds number. And higher the roughness, higher is going to be the friction factor. So any questions about the Moody's friction factor chart? Is the interpretation of the chart okay? Okay. So now how can we use F in our problems? So F is used in this way. Delta P by rho is 4F L by D into V square by 2. So this is nothing but this is showing the pressure drop. So in order to calculate the pressure loss as a result of the friction, this is the equation we are going to use. 4F L by D into V square by rho. This is also written as HFS. HFS. So where HF stands for friction and the S stands for skin friction. So this is another important point. You have to note that HFS corresponds to the losses only because of skin friction. And there are two kinds of friction which occur. One is skin friction and the other one is form friction. So whenever you have a pipe and if you're looking at fluid flow near the wall, there is a drag force which the solid exerts on the fluid. This is called skin friction. And let's look at another case. Whenever you have, so you're going to have a pressure drop. Pressure is going to drop. Whenever you have an expansion, so what is going to happen is the fluid which is going here at some point forms recirculations. Similarly on the upper surface as well. Because of these recirculations, there is going to be a pressure drop again. But this pressure drop is not because of the presence of the wall, but it is because of the formation of a secondary flow or vortices. And this friction is known as form friction. So HFS accounts only for skin friction. It does not take into account the form friction. So you need a separate term to account for form friction again. And in some cases, for example, when you have a sudden contraction or a sudden expansion, let us look at a sudden expansion first. So when you have a sudden expansion, for all these cases, sudden expansion and then sudden contraction, or when you have a U bend, all these cases, or you have a T valve, all these cases involve losses. So the losses are accounted in this manner. So you use a velocity head. Loss is equal to, so loss in each case is equal to KL into V square by 2G. Summation KL into V square by 2G. So KL has a different value for each situation. For example, KL could be 0.5 for this bend. KL can be pretty high, 1.5 for a T junction. Similarly, you can also develop an analytical relation for KL using mass balance and momentum balance for expansion. So when it expands, it looks like this. And the relation is KL is equal to, I think it's, I'm not sure. I think it's, you can check this. It's 1 minus SA by SB whole square. You can check the derivation and the KL value for this case, sudden expansion. And in case of sudden contraction, you cannot apply the Bernoullis equation, or you cannot analytically obtain the KL coefficient. The reason is because the flow when there is a sudden contraction is more complicated. So I'll show you both the cases comparatively. This is a contraction, and then you have the second case, which is an expansion. So when you have an expansion, the fluid straight away expands. And this region has backflow. Vortices are formed in this region. In case of a sudden contraction, so the fluid initially contracts but then it expands. So the flow is more complicated than a simple expansion. So you have backflow over here. You also have slight backflow over here. So this makes it difficult to obtain an analytical relation. So therefore, we use an empirical relation, which is for KL, which is zero point 0.4 into 1 minus SA by SB. SA is the smaller area and SB is the larger area. So now we can look at this problem, which involves losses as well. Okay. So go through the problem. Okay, now let us see how we can proceed with this. So the flow rate is given. Flow rate is 0.22 meter cube per second. And from a reservoir at a ground level to another reservoir at a height h. So this is a reservoir and this is another reservoir which is located at a height h. And the diameter of the pipe is also given. So the diameter of the pipe is 0.2 meters. And the power input to the pump is 90 kilowatt. And what is the efficiency? The efficiency of the pump is 0.75. And the F value is also given. F is 0.004 and the density is 1000. So the first step would be to write down the terms of the Bernoulli equation. So it is going to be, and both the reservoirs are open to atmosphere. So it's going to be P1 by rho plus V1 square by 2 plus GZ plus eta into WP should be equal to P2 by rho plus V2 square by 2 plus GZ2. Once again, similar to the previous problem, if we take the reference level to be this, and this is z is equal to 0, then this is going to become z is equal to h. So z1 is 0 and z2 is h. And can anyone tell me the values of P1 and P2? Do we know P1 and P2? Pranit, any idea of about P1 and P2? Okay, if you read the question properly, they have mentioned that both the tanks are open to the atmosphere, which means the atmospheric pressure is going to be, so the pressure is going to be PA, P atmosphere in both the cases. So you might argue that the pressure here is going to be PA, then the pressure here will be PA plus rho air into G into H. But rho air is so small that you can essentially neglect this term. So it's essentially PA and PA. So P1 is PA and P2 is PA, and both of these terms will get cancelled. And then you have V1 square and V2 square. Similar to the previous problem, if you're using a pipe of having the same diameter throughout, by the continuity equation for incompressible flow, you need V1A1 should be equal to V2A2. So, which means A1 and A2 are same. So V1 and V2 should be same. These two terms are going to get cancelled. Oh, and also you have losses in this problem. So you have to include HF as well. So GZ1, Z1 is 0. So essentially you are getting eta WP is equal to GZ2 plus HF. Now let us look what this intuitively means. It means whatever work your pump is doing, your pump needs to do certain amount of work, and this work will be used in overcoming the gravitational potential and also in overcoming the losses. So that is the meaning, a physical meaning of this equation. So let us calculate eta WP. So how can we calculate WP? What is WP? So as we have discussed earlier, WP, every term in this equation corresponds to unit mass of the fluid. So WP is the energy per unit mass of fluid. The energy input to the fluid per unit mass by the pump. But we know that the power is 90 kilowatt. So which is 90 into 10 power 3 joule per second. And we also know that the fluid is flowing at a rate of 0.22 meter cube per second. So 0.22 meter cube per second, if you convert it into kg, it is going to be 0.22 into 10 power 3 kg. So by dividing these two, you'll be able to get the value of WP. And WP is going to be in joule per kg. Because this is in kg per second. So second and second will get cancelled. You have joule per second. So can you tell me the value of WP? What is the WP you got? I got WP to be 409.1. 409.1 joule per kg.
Same, Anna.
Okay, nice. So, and let us calculate HF. What is HF? HF is equal to 4F L by D into V square by 2G. Sorry, V square by 2. There's no G. So do we know the value of F? It has been given in the question. 4 into 0.004 into L. Do we know the length of the pipe? Okay, so the length of the pipe isn't given, which means you can take h to be the length of the pipe. So it's simply this system. You're just transporting the fluid and immediately dropping it into the second reservoir. So L is going to be h, L by D. So 4F h by, do you know the diameter is given, D, 0.2, into V. We can also calculate V because we know the flow rate and we also know the diameter. So that knowing the diameter is going to give us the cross-sectional area. And velocity is nothing but flow rate divided by the cross-sectional area for flow. So from there, you're going to calculate the velocity and use the velocity over here, v square by 2. Can anyone tell me this term, the HF term, simplified version of HF term? This is what I got. HF is 1.962 times h. Did anyone get the same thing? Bhavana, Praneeth, Prarthana. Okay. So in case this is correct, then the height is going to be 0.75 eta WP. 0.75 into 409.1 should be equal to GZ. So G is 9.81 into Z. Z is nothing but H. Z2 is H plus 1.962 times H. So from here you can calculate H. So the height is approximately 26.1 meters. సో ఈ ప్రాబ్లం అర్థమైందా అందరికి? ఎనీ డౌట్స్ ఇన్ దిస్ ప్రాబ్లం ఎనీవేర్? ఈ క్యాలిక్యులేషన్ ఆర్ దిస్ క్యాలిక్యులేషన్? ఓకే,
క్లియర్ అన్నా.
ఓకే. ఓకే, ఇది ట్రై చేయండి. అసలు చేయడానికి ఏం లేదు, జస్ట్ లుక్ ఎట్ ఇట్ అండ్ టెల్ మీ వాట్ యూ థింక్ ద ఆన్సర్ ఈస్. This is entirely based on the Moody's friction factor chart. Take 2 minutes to think about it, and everyone let me know your answers one after the other after 2 minutes. So ready with your answers? Cheppandi one after the other. Bhavana, what do you think? ఏది కరెక్ట్ అయి ఉంటుంది? So let us look at it step by step. First set చూస్తే, for a Reynolds number of 100 and zero roughness, Reynolds number 100 అంటే what type of flow can you expect in a pipe? Is it going to be laminar or turbulent?
లామినార్ ఫ్లో.
సో లామినార్ ఫ్లోకి ఎఫ్ వాల్యూ ఎంత? 16/NRE కదా. సో 16/NRE is going to be 0.16. So దాంతో you can eliminate set 2 and set 4. The answer should be either set 1 or set 3. So next value తో you have no use because set 1 ki set 3 has and both have the same value. Then look at the next set, 10 power 5. So same Reynolds number, 10 power 5, 10 power 5. Reynolds number సేమ్ ఉన్నప్పుడు రఫ్నెస్ పెరిగితే వాట్ షుడ్ హ్యాపెన్ టు ద ఫ్రిక్షన్ ఫ్యాక్టర్? షుడ్ ఇట్ ఇంక్రీజ్ ఆర్ షుడ్ ఇట్ డిక్రీజ్ ఆర్ రిమైన్ కాన్స్టెంట్? సో రఫ్ గా ఉంటే ఫ్రిక్షన్ ఎక్కువ ఉంటుందా తక్కువ ఉంటుందా?
ఉంటదన్న.
ఫ్రిక్షన్ ఎక్కువ ఉంటుంది. సో ఫ్రిక్షన్ ఫ్యాక్టర్ విల్ బి మోర్. సో సెట్ 1లో చూస్తే ఫ్రిక్షన్ ఫ్యాక్టర్ చేంజ్ అవ్వట్లేదు అసలు. ఇట్ ఈస్ రిమైనింగ్ 16 into 10⁻⁵. Set 3లో the friction factor is increasing slightly. So set 3 is the right one and the remaining all are wrong data. ఈ క్వశ్చన్ అర్థమైందా అందరికి? The approach for solving this?
Yes, Anna.
Okay. Okay, so try this problem. Or do one thing, దీన్ని స్క్రీన్ షాట్ తీసుకోండి. టేక్ ఎ స్క్రీన్ షాట్ ఆఫ్ దిస్ ప్రాబ్లమ్, ట్రై చేసి అండ్ లెట్ మీ నో ఇన్ ద గ్రూప్ ఏ ఆన్సర్ వచ్చిందని. స్క్రీన్ షాట్ తీసేసుకున్నారా అందరూ?
Yes, Anna.
Okay. Let us look at an important concept called net positive suction head using this problem. So, అసలు what is net positive suction head? Net positive suction head. So let us say this is our system where we have a reservoir and you are sucking in water from the reservoir or any fluid, need not be water, and then you are transporting it to a higher potential. This concept comes into picture only for volatile fluids. Volatile fluids, which means which have the tendency to vaporize or which have the capability to vaporize at operating conditions. For example, water, it could be oil. And for non-volatile fluids, this concept is not very important. So what is net positive suction head? So when you have a pressure P1 here, for the pump to suck the fluid, this is PS. PS stands for the suction pressure, which is the pressure with which the pump draws in the liquid. And this is the outlet pressure, and you have the final pressure P2. And PV is the vapor pressure of the fluid. So usually suction pressure has to be low. Only when it is low, it is possible for the fluid to flow from P1 to PS. So fluid flows in a direction of decreasing pressure. So from high pressure to low pressure, which means PS has to be obviously lower. But inside a centrifugal pump, so centrifugal pump consists of a rotor. And the fluid flows here into the rotor, and the rotor adds more kinetic energy or increases the pressure of the fluid and sends it outward. So near the rotor blades, the fluid experiences a pressure which is much lower than the suction pressure. So suction pressure is the pressure somewhere, let us say this is our pump. So the suction pressure, and the suction is from this here, and the discharge is from here. So the pressure here is going to be PS. And the pressure here, let us call it PB. So B stands for pressure at the blade. So the pressure at the blade, it is possible for the pressure at the blade to be much lower than PS. So there comes a condition where if PB becomes too less. It becomes less than the vapor pressure at this temperature. Vapor pressure is a function of temperature. If it becomes less than the vapor pressure at this temperature, the fluid is no longer to remain in a liquid state. It is going to instantaneously vaporize. So whenever you have a fluid vaporizing, uh, we know that the density of water. So density of water is 1000 kg per meter cube, which means the specific volume of water is 0.001 meter cube per kg. That is, if you have 1 kg of water, it is going to occupy 0.001 meter cube. Similarly, if you look at the density of water vapor, it is around 1 kg per meter cube, which means the specific volume is 1000 meter cube per kg. So initially, if you had water in this place, the, wa the water was occupying a specific volume of this much, 0.001 meter cube per kg. And as soon as the pressure falls below the vapor pressure, the water instantaneously vaporizes to vapor. So the vapor now has a very high specific volume, which is 1000 times more. So when a small fluid element is suddenly expanding to 1000 times its size, it is accompanied by uh, great pressure in all directions. So this pressure is transmitted to these blades. So the blades are made up of metal, and this causes corrosion of the metal. And sometimes what happens is that these once they expand, these air bubbles or these water bubbles, water vapor, when it moves back to a region of lower higher pressure, for example, it moves here, from here you have the water bubble formed, and now the water bubble has traveled here, where the pressure is greater than vapor pressure. So what happens is it transforms back from vapor to liquid, and this transformation is very violent. So you have a bubble. This is the water vapor bubble. This is at a condition P less than PV. As soon as it goes to a condition where P is greater than PV, something happens to it. It forms into a donut shape, and there is a high pressure water jet, liquid water jet, which flows through it. And whenever you in this direction, and whenever you have any metal object right next to it, it strikes the metal object with such great force and velocity that it gets corroded. So you want to prevent this at all costs. This phenomena is called cavitation. And you want to prevent cavitation. So if you want to prevent cavitation, you put a safety standard. That is, if you definitely know that the pressure inside the impeller or pressure inside the pump is going to be less than PS. So if you make sure that the pressure does not fall below PS or some value P, some safety value P star, if you make sure that the pressure is above P star, then you will prevent the fluid from vaporizing inside the pump. In this way, you can prevent cavitation. You can avoid cavitation. So net positive suction head is defined as PS minus PV. This is NPSH. Is the concept clear to everyone? Why we have a concept of NPSH, net positive suction head?
Yes, sir, yeah, clear.
Okay. So we will look at it using an example. You may find it more helpful that way. So this is the problem we have. A storage vessel exposed to atmosphere at an absolute pressure of 10 per 3 meter has a diameter of 3 meters. So I hope everyone has read the question. Now let us solve it. So we have a tank which is filled up to 2 meters with water, and the atmospheric pressure PA is 10.3 meters. So what does this mean? 10.3 meters. This means the pressure at any point is equal to the pressure of a column of water. A column of water having a height of 10 power 3 meters, 10.3 meters. So if you know density to be 1000 and G is 9.8, you can calculate the pressure at this point using rho GH. So this is nothing but another way to express the pressure at a point in terms of height of a liquid column. And then you have a pump, and this is 5 meters. So if this is 5 meters and this is 2 meters, from the free surface, okay, let us apply a Bernoullis equation now. So the pressure, we know that the pressure at the suction, let the pressure at the suction inlet be PS. And the pressure here be, we know the pressure is PA. So the equation is going to be PA by rho G plus PA by rho G plus V1 square by 2G plus GZ1. And remember, can anyone tell me, should we write the pump, should we include the pump in this equation or not? Bhavana, what do you think? Should we also write eta WP?
Yes, Anna.
Why do you think we should write eta WP? So if you look at it carefully, the streamline or the system which I have chosen begins here and ends right at the inlet of the pump. But there is no pump in between. So therefore, you don't have to include the pump. In case I was taking this as the ending point, then you have to include the pump. Is that clear?
Yes, Anna.
Okay. So this is equal to, what is PB? We know PB is PS. PS by rho G plus V2 square by 2G plus GZ2. And you also have the friction losses, HF. Now you can ignore the velocity heads, V1 and V2. Now what is PA by rho G? PA by rho G is nothing but 10.3. What is GZ1? So if you choose this to be Z1 equal to 0, then this is going to be Z2 is equal to 5 minus 2, which is 3. So 10.3 plus this is going to be 0. 10.3 should be equal to, you have PS by rho G plus GZ2. No, this is going to be just Z2, not GZ2. Just Z1 and Z2 plus Z2. Z2 is going to be 3. And what are the friction losses? So the frictional head loss is 2 meters of water plus 2, which means PS by rho G is equal to 10.3 minus 3 minus 2, which is 5.3. So essentially the suction head is 5.3 meters of water. But they have mentioned that the vapor pressure of the liquid at the temperature of operation is 3 meters. So from these, you have to subtract 3 meters to get the available NPSH. So 5.3 minus 3, which is 2.3. That is the available NPSH. Is this clear?
Yes, Anna.
Okay. So that's it for today's class. We have mainly focused on the Bernoullis equation and also a problem on NPSH. Thank you, everyone.
Thank you, Anna.
Done.